Yesterday, we talked about the cross product, where we take a vector, multiply by another vector, and come up with a vector. The important thing that we noted was that the cross product of a couple of vectors was perpendicular to both the vectors in the product. U cross V is normal to the plane containing U and V. What this means is that we have a new way to describe a plane in R3. We can describe an entire plane in R3 by saying it's all the vectors that are perpendicular to this normal vector. So the normal vector is a way to describe a plane in R3. Any questions about that before we do an example? Cool. So let's suppose that we have a plane containing some points. Let's suppose that we have a plane containing these 3 points. 2 vectors will determine a plane, 3 points will also determine a plane. Because we can take these 3 points and make 2 vectors out of them. So let's suppose we want to find a vector normal to the plane containing these 3 points. What we can do is take the 3 points and form 2 vectors. We pick one of the points to be the vertex. It doesn't matter which one. We've got 3 points, P, Q, and R. And we can make 2 vectors. So I can go PQ and PR. Those will be 2 vectors. They have P in common. I can go QP and QR, or RP and RQ. So anyway, we want to make vectors. I am going to go with PQ and PR. So notice that the points PQ and R just have regular names, but PQ is going to be a vector, so I'm going to put an arrow over the top of it. And then PR will be my other vector. So there are my 2 vectors. I need to come up with vectors. I know the endpoints of the vectors. So I'm just going to think about what vectors represent. They just represent displacement. So if I start at P and end up at Q, I can make a vector out of that. So let's make the vector PQ. Notice that there's no change in the X. X starts at 1, ends at 1. So for an X displacement, there is 0 in the X. If Y starts at 0 and ends up at -1, I just do -1 minus 0, -1. And then if Z starts at 1 and ends at 3, we can say that the displacement in the Z direction is 2. 3 minus 1 is 2. So just subtract to find the components of the vector PQ. We'll do the same thing with the vector PR. I just need to indicate that direction. So I'll just subtract components like we did before. So PR if we start at P and end at R, the X increased by 2. So we're going to have to do a +2 in the X. The Y's don't change. Y starts at 0 and ends at 0. So there's no change in the Y. And if P starts at 1 and ends at -1, then that's a change of -2. I can also just subtract where we ended up, -1, minus where we started, 1, so -2. Note that we're getting this just by thinking about what we want. We want to know how things change from starting off P and ending up at Q, then starting off at P and ending up at R. What we want to avoid is trying to have some list of formulas for how to remember things. Like I said before, when we talk about slope as rise over run, if you understand the concept of slope, you don't need the formula y2 minus y1 over x2 minus x1. It only gets in the way. This is why we should avoid formulas whenever we can, because they tend to get in the way. Now, what we're going to do is find the cross product of PQ and PR, and then that'll give us a normal vector that'll describe everything in the plane. If I calculate PR cross PQ, that'll be starting off at PR and bending towards PQ. Our normal vector will come out of the paper into the camera. That sounds dangerous. So what we can do is do PQ cross PR. That means we'll start pointing in the PQ direction and bend towards the PR direction. Our normal vector will go down into the paper. That's much safer. I don't want to lose an eye because I put the cross product in the wrong direction. So let's calculate PQ cross PR, but we should understand where that vector is going to be pointing. So let's do PQ cross PR. So it's going to be normal to the vector PQ and PR, so normal to the plane containing those two vectors. And if we do PQ cross PR, that'll put the normal vector pointing down into the paper. So I'm going to calculate the determinants. I hat 0, 2, j hat, -1, 0. K hat 2, -2. So I'm going to calculate the coefficient of I. This could be a disaster. It's going to be because I'm doing calculations. So we're going to have -1 times -2 minus 2 times 0. So -1 times -2 is 2. So I think I got it 2i. This is assuming I did calculations correctly, which is a dangerous thing to assume when I'm in charge of the calculation. The next minor is going to be 0, 2, 2, -2. So I'm going to take out this middle column. And so I'm going to have 0 times -2 minus 2 times 2. 0 times -2 minus 2 times 2. That's going to be 0 minus 4. It's going to be a -4. But in the cross product, we're doing a determinant, and J is in the second position, so we change the sign. And finally, in the Z direction, for K, I've got 0 times 0 minus a -1 times 2. So 0 times 0 minus a -1 times 2. So I get 0, negative times negative is positive. I'll get plus 2K. We can do a quick dot product check to make sure that we have calculated the cross product correctly. We can check to see that this is perpendicular to both PQ and PR. So we can do a quick dot product check. So 2 times 0 plus 4 times -1 plus 2 times 2 is equal to 0. So I'm just doing a dot product check. So PQ cross PR that we calculated is perpendicular to PQ. Let's see if it's perpendicular to PR. So 2 times 2 plus 4 times 0 plus 2 times -2. Looks like I was way more accurate than I was yesterday. So here's a vector normal to the plane containing PQ and PR. Here's a vector normal to the plane containing the 3 points 1, 0, 1, 1, -1, 3, 3, 0, -1. Sometimes we give these, we call these normal vectors N. N for normal. Because writing PQ cross PR all the time would be cumbersome. Any questions? Is everybody okay? Second time in 2 days, we calculated the cross product by hand. It's gonna make for some riveting YouTube. This is why I have so many millions of followers. I'm just kidding. No one wants my videos. I can get away with an awful lot. Now that we have this information, we can use it to find the equation of a plane. This is something that we might be interested in. Because one of the big questions that we ask in calculus is what is the equation of a line tangent to a curve at a given point? And in multivariable calculus, that upgrades to what is the equation of a plane tangent to a surface at a given point. Yesterday, I advertised that we could describe a plane with one vector, normal. We could just normal to the plane by saying, find the plane where that's of all the vectors that are perpendicular to this one vector. And that would be used to describe the plane. So So there should be a way to describe a plane using a given point, x naught, y naught, z naught, and with a normal vector. I can't remember the notation that this book uses. For what is it named? The components of the normal vector. I want this one. Oh, hey, there's a variation on the problem that we're doing. What do we call the components of the normal vector. I'll make them up. That's what I always wish they were called anyway. So let's suppose we have some normal vector nx, ny, and nz. The equation of a plane containing the point x naught, y naught, z naught that has this normal vector is given by so we can take our slope, it's just like putting together the slope and a point. Notice that this is in a slightly different form than we had for, this is in a slightly different form than our y equals mx plus b form, or z equals z naught plus m times x minus x naught plus n times y minus y naught. We don't have it in a function format. We've got it in the form of an equation. And we're going to want to see how this corresponds to linear equations with two variables. But if we want to find the equation for the plane containing the points P, Q, and R that we had before, now that we know the normal vector, we can just put things together into this. So for example, if we want to find the equation of the plane containing P, Q, and R, since we already have the normal vector, 2i plus 4j plus 2k, since we already have that normal vector, we can just put things together with into the equation. We could use any one of the points P, Q, and R. So note we already have the normal vector. We already have the normal vector. The point P is 1, 0, 1. So I'll take nx 2 times x minus x naughts plus ny times y minus y naughts plus nz times z minus z naught. This is just one option. We had two other points. This is using the point P. Using the point Q, we would have 2 times x minus 1 plus 4 times y minus a negative 1 plus 2 times z minus 3. And our third option, using the point R, we'll have x minus x naught plus 4 times y minus y naught plus 2 times z minus z naught. So we're making the claim that all three of these equations tell us the same plane. We just have different starting points. Notice that anything that has to do with the direction, how things are changing, how x is changing, how z is changing with respect to x, how z is changing with respect to y, all that stuff is constant. The coefficients are all the same. We just have different starting points. So if I multiply each of these equations out and think about what's going on at the origin, then we should get the same equation. So if I multiply this out, let's see, I get 2x. This will be a -2 plus 0. -2 minus 2 is going to be -4. So if I put it on the other side, that'll give us a 4. So that looks like we'll have what? 2x plus 4y plus 2z is equal to -2 minus 2, put on the other side, 4. If we look at the second equation, 2 times -1 is going to be a -2, but then 4 times 1 is +4. That gives us a +2. But then the last one is 2 times -3 is -6. Down to -4, put it on the other side, it's 4. And then the same thing happens in the third equation. So all three equations can be summarized with 2x plus 4y plus 2z is equal to 4. That would be the most convenient answer.
Oh, to simplify like
To multiply it all out.
okay.
And so this would be the equation of a plane. We can see that it's going to be an equation of a plane. We know it's going to be we can see that it's a linear equation. The three variables x, y, and z are all exponent of 1. So degree 1 all the way through. We know it's going to be a plane because it's a linear equation in 3 variables. And our 3 linear equations look like planes. If I want to describe just a line in R3, we have to do something else. We don't get to use an equation with 3 variables. Questions?
So the normal is perpendicular.
The normal is perpendicular to the plane. So the other thing that we can do, now that we have this equation down here, is we can solve this for z and see what the function looks like. We can solve this for z and see what it would look like as a function. So let's do that. So let's solve this for z. First of all, I'm going to divide everything by 2. That's going to be x plus 2y plus z is equal to 2. And I'm going to subtract the x and the y terms. And so we can say z equals 2 minus x minus 2y. So here's another option for the equation of that plane.
Which one would you prefer?
Whichever one shows up first. So unless I specify a particular one, either in function formats or in this standard formats, it would probably be one of these two. Mostly because there are going to be too many choices for your point slope equations. How's everybody okay? They look fascinated. We notice some more things here. Remember, when we look at this equation of the plane, z is equal to 2 minus x minus 2y, We read that -1 coefficient of x as how z is changing with respect to x. That's the rate of change of z in the x direction. Z is decreasing by 1 when x increases by 1. We also see the coefficient of y in this function format when we're in this slope-intercept format. The coefficient of y is -2, so that's the rate of change of z with respect to y. dz dy is equal to -2. Any questions? How's everybody okay? These two forms correspond, or three forms, I guess we could say. These three forms, no, I didn't write the other one in point form. These two forms, the blue and the green form, correspond to the linear equations that we're familiar with when we have two variables. So this 2x plus 4y plus 2z equals 4, that corresponds to the standard form of the equation of a line. And z equals 2 minus x minus 2y corresponds to the slope-intercept form of a line. Notice that in that green equation, if x and y are both 0, then the z-intercept is equal to 2. So that tells us point 0, 0, 2. And we just mentioned that the coefficient of x is how z is changing in the x direction. Coefficient of y is how z is changing in the y direction. Any questions? What we want to be able to do, the reason that we want to be able to find equations of line like this and just lines like this, and recognize that the coefficients of the equation of the plane in standard form are the components of a normal vector. This is important because we want to be able to describe planes. One of the big things that we do in calculus is find the equation of a plane tangent to a surface at a given point. We know we need to do that with derivatives. We haven't talked about finding derivatives and plugging in those values to get those slopes. But the process is going to be the same that we learned back in Calc 1. Take the derivative with respect to x, plug in the point that you care about. In this case, you have three choices. Plug in the point that you care about. That's the rate of change of z in the x direction. Take the derivative with respect to y, plug in the point that you care about. That's the rate of change of y in the x direction. You are finding the components of a vector normal to the surface. Questions? Comments? Deep thoughts? My question is, in a class like this, where there's fewer people than there are seats, I guess that's always the case, but so much fewer people, so many empty seats. Is it easier or harder to skip class? That's the question that I wonder about. You don't have to answer that, because I know y'all think you know what the answer is by saying, oh, no, we would not skip class. And then some of you, like maybe straight out of high school, is like, well, wait a second, skipping class is an option. It's like, oh yeah, I never follow up on that. Like if you send me an email and tell me that you're sick, I'm just going to believe you, especially now. If you come in here all sniffling and stuff, I'm just going to throw you out. It's like, we can't have no sniffles. But I'm wondering, because this class is like 20, my 8 o'clock class is like 40. And what I want to do is I want to track how many people skip class on any given day, kind of find average to see if it's easier or harder to skip class. Now, it might be that you might want to take into account like the level of the classes, but 8 o'clock class is Calc 2. It's like, and then this class is Calc 3. So y'all are pretty much at the same level. The reason this class is so much smaller is this class is a lot less required at the schools to which you're going to transfer. You know what I mean? Anyway. What's that? Yeah, there are some business schools out there that say you need Calc 2. There are some business schools out there that just really don't understand how math works. And they say, no, you can't take the business calculus class you've got to take this calculus class. And then the students are like, oh, but that one is at this school, that would be the 240 series and the 250 series. Y'all are the 250 series at the science and engineering conference. If you're a business major, I'm sorry your school is making you do this. But your school has some very high-minded ideas about what it provides. You know what I mean? So why wouldn't they want you to take a calculus class that's like geared towards business application? Because in the 250 series, they're like, oh, let's use some physics application. You know what I mean? And then people are like, oh, well, why don't you just do all of them? It's like, oh yeah, that's right. We do have an infinite amount of time. Oh, and second of all, how much physics am I going to have to know to teach calculus? I'm here to teach calculus. How much business am I going to have to know to teach calculus? You know what I mean? This is honestly what people expect out of math teachers. You know all those things that we use math for? Yeah. You have to know all of them. To which I usually respond, I'm here to do math. I mean, I will pillage physics, but I want very little out of it. I don't want to actually explain how physics works. Number one, it's not my job. And number two, I'm not qualified to do that. But I will watch a physics class and be like, oh, work is equal to force times distance, say that's multiplication. I can use that over here. Because integration is multiplication where one of the factors is variable. I'm going to take the force and make it variable. You know what I mean? But then students are like, well, how do you explain the physics? And I'm like, well, I don't. You're going to need to go talk to your physics people for that. When am I ever going to do this? You're going to have to go talk to engineers. You know what I mean? This is finding the equation of a plane. We are going to use this. Once we get the hang of this, we're going to use this to find the equation of a plane tangent to a surface at a given point. And the reasons that we want to be able to do that are the same reasons that we wanted to find the equation of a line tangent to a curve at a given point. The tangent line is the best linear approximation to a curve at a given point. And so this plane is the best linear, this is a plane. So I don't need approximation. But if we have some surface, the tangent plane will be the best linear approximation. So if we can't evaluate the function precisely, we can get an idea about what's going on in a small area around a particular point. Exactly the same way that we did in Calc 1 when we looked at the tangent line at a point. All right. I've put up a new quiz. And the quiz is to find equations of some functions given a contour diagram. And the contour diagrams that I gave you are a bunch of parallel lines. And the handwritten value, I was trying a lot. This is an old test. This was a test before when I did tests. There, now it wasn't a test. I was trying so hard to figure out how I'm going to get the z values onto my graph. And I'm like, well, you know what? I'm just going to write them. So, low text. But I want you to find an equation for each of these. Each of these contour diagrams. They represent functions. I want you to find equations for these functions. Now, this first one's a little bit tricky because you see all those parallel lines. You might think, I see parallel lines. Is this a plane? But then you notice it's not a plane. It's like 12, 5, 0, -3, -4, -3, 0, 5, 12. That's not a plane. Otherwise, those would be evenly spaced apart. Or not evenly spaced apart. The z values would have a constant rate of change. Because planes are linear functions. And linear functions have constant rates of change. The other two are based on circles. So you got to think about what kind of functions are going to have circular contours. And then notice that the change is in
where these values are. So notice that the first one just goes 1 through 8, but here they go 1, 4, 9, 16, 25, and so on. Any questions? Comments?
Snide remarks? All right, so that's going to do it for today. That's going to do it for this week. Everybody have a good weekend. I'll see you on Monday. And thanks for playing.